तस्य रूपमधिकम् प्रच्छन्नगुप्तं धनम् विद्या भोगकरी यशः सुखकरी विद्या गुरुणा गुरुः विद्या बन्धुजनो विदेशगमने विद्या परं दैवतम् विद्या राजसु पूज्यते न तु धनम् विद्या विहीनः पशुः विद्या प्रशस्यते लोकैः विद्या सर्वत्र गौरवा विद्यया लभते सर्वम् विद्वान् सर्वत्र पूज्यते ज्ञानेन सदृशं पवित्रमिह विद्यते न हि ज्ञानेन सदृशं पवित्रमिह विद्यते न हि ज्ञानेन सदृशं पवित्रमिह विद्यते।
Professor Dr. Dattatray Nerkar is the Vice Principal and Head of the Department of Physics at PTVA's Sathaye Clg Autonomous. Having had a distinguished career, his teaching experience expands up to an impressive span of 35 years. He holds a Ph.D. degree as well as an MPhil degree in the subject of physics. His major academic areas of interest include conducting polymers, nanocomposites, nanostructured metal oxides, gas sensors, antibacterial activities, and healthy growth of plants. 31 of his research papers have been published in Thomson Reuters listed journals and UGC Care listed journals. Also to his credit are 5 authored books and 2 chapters in books. He has been an active researcher throughout and has presented his research paper at various international and national conferences. He has been regularly invited as an external referee for examining PhD thesis and viva voce at Manasthali University, Rajasthan, Savitribai Phule University, Pune, and Kavayatri Bahinabai Chaudhary, North Maharashtra University, Jalgaon. He has also been a distinguished member of the editorial board for the evaluation of research papers in 3 journals indexed in the Web of Science or UGC listed. To his credit, he is a Vice Chancellor nominee on the Academic Council for VES Arts, Science and Commerce College, Chembur. Besides, he has served as the Vice Chancellor's nominee on the Board of Studies of various autonomous colleges across Mumbai. He has conducted 2 minor research projects granted and funded by the Mumbai University. Dr. Nerkar has also been a recipient of the prestigious national level Thakur Awards for Excellence and awarded as the Excellent IQAC Coordinator for the year 21-22. Also, he has received the prestigious Adarsha Shikshak Puraskar Award from an NGO Mahavir International Nashik for the year 2019. Welcome Vidyavachaspati Dr. Dattatray Nerkar.
Hello everyone, Namaskar. My name is Professor Dr. Dattatray Nerkar and I work at Sathaye Clg in Vileparle as a member of Physics Department. It gives me immense pleasure to speak about the research I have undertaken for my doctoral degree. A research journey is a series of milestones for an individual, starting with choosing a research topic and ending with turning into thesis. We get sentimental and remember every challenging experience as well as the successful times. I am grateful to Parle-Tilak Vidyalaya and Sathaye College for giving me this chance to cherish the occasion once again, and I share with you the experimental findings from our lab. My doctoral thesis was titled Synthesis of Smart Polymetric Materials for the Development of Gas Sensors. Normally, polymers do not conduct electricity. It is the same insulating property that made them attractive in many industrial applications. The vast development in the electrical field would not have been possible in absence of plastic. One cannot imagine of electrical cables without polymer insulations. However, attempts were made to impart electrical conductivity to polymer films by several different methods with the aim of developing flexible conductive materials. The Nobel Prize in Chemistry was awarded in 2000 to Alan Higger, Alan McDiarmid and Hideri Sirikawa for recognizing their path-breaking discovery of development of electrical conductive polymers. Even after 47 years of the discovery, the field of conducting polymers still remains a subject of intense research. Class of advanced materials holding a major place and pivotal role in the field of material science. Electrical properties of conductive polymers can be fine-tuned using the methods of organic synthesis, so named synthetic metals. Applications of conductive polymers are very much there. Properties like lightweight, lower energy requirements and design flexibility with a good range of conductivity have made conductive polymers attractive in large number of applications. Some of the important applications are like sensors, data storage devices, supercapacitors, photovoltaic cell, actuators, transistors, drug delivery, corrosion protection, and the list is non-ending. Solids can be classified as metals, semiconductors or insulators based on their conductivity. Conjugated polymers comprises a wide range of conductivity. The conductivity of conductive polymers can be compared with quartz, that is insulator, or copper, that is conductors. Polymers may also have conductivity corresponding to those of semiconductors. The best known and most studied conductive polymers are polyacetylene, polyphenylene, polypyrrole, polythiophene, polyaniline, etc. Polypyrrole was chosen among the known conducting polymers for the research study due to following reasons. Among the known conducting polymers, polypyrrole is of particular interest owing its high conductivity, stability in oxidized state, interesting redox properties and simplicity of synthesis procedure. Conductive forms of polypyrrole are prepared by oxidation of the pyrrole, which can be achieved using ferric chloride. The main objective of this research work was to synthesize exclusively conductive polypyrrole, polypyrrole polyvinyl alcohol composite films and polypyrrole silver nanocomposite. Their characterizations and conductivity measurements, as well as to explore possibility of utilizing them in gas sensing applications. Let us discuss the work plan in details. It was done in 3 phases. In phase 1, the synthesis was done in details to develop novel chemical route to synthesize conducting polypyrrole, polypyrrole polyvinyl composite films and polypyrrole silver nanocomposite without any impurity or byproduct. In phase 2, whatever samples we have prepared, their characterization is essential to know about their purity. So we have done SEM, TEM, FTIR and XRD of the samples, as well as if they are conducting polymers, then we need to check their DC electrical conductivity. So we have checked DC electrical conductivity as a function of temperature. And finally we come to the application part in work plan for investigating their gas sensing properties. They were tested for gases like carbon dioxide, nitrogen dioxide, hydrogen sulfide, ammonia and liquid petroleum gas. Once they are tested for these gases, then we need to know response and recovery behavior of the gas sensors, repeatability and selectivity of the fabricated sensors, as well as to formulate possible mechanism of gas sensing. Now let us start the discussion with phase 1 of experiments. The first batch was of synthesis of polypyrrole. A series of reactions were conducted to prepare the black polypyrrole powder. The procedure in short is like this. 1 molar pyrrole solution was prepared using distilled water and cooled in ice bath with continuous stirring. The pre-cooled aqueous solution of FeCl3 was added dropwise to the pyrrole solution. The polymerization was conducted for a period of 5 hours under constant stirring in an ice bath. The mixture was allowed to settle for 24 hours to ensure complete polymerization. The product was filtered under reduced pressure, washed with distilled water until the filtrate became colorless and dried under vacuum at room temperature. Polypyrrole powders with different molar ratio ranging from 0.5 to 3 were prepared. The picture shows the different powders, polypyrrole powders prepared of different molar ratios. Batch 2 of synthesis experiments is of polypyrrole polyvinyl composite films. In this, 4% weight to volume PVA solution was prepared. It was then stirred vigorously at 70 degrees centigrade for 3 hours on a magnetic stirrer, which was then left to cool at room temperature. The PVA solution, double distilled pyrrole, was added. Polymerization of pyrrole was carried out using oxidizing agent ferric chloride. The oxidizing agent was added dropwise to the polypyrrole polyvinyl solution. The homogeneous black colored solution was obtained. Films of the solution were prepared by pouring a certain small portion into a glass petri dish. Solvent evaporated on its own, left to dry at room temperature. Ripe of the freestanding PPY PVA composite films from the petri dish. PPY PVA composite films of different molar ratio ranging from 0.1 to 1 were prepared. Picture shows the different films prepared under this scheme. Batch 3 of synthesis was polypyrrole silver nanocomposite. The procedure in short goes like this. The PPY AZ nanocomposites were synthesized by in situ chemical oxidative polymerization. In a typical synthesis experiment, 100 ml of silver nanoparticle colloidal solution was cooled in an ice bath. 1 ml of pyrrole was then added dropwise to this solution. The aqueous solution of FeCl3 was pre-cooled and added dropwise to the above solution. The color of solution changes from golden yellow to grey and then finally to black. The obtained mixture was allowed to react for 5 hours with slow stirring in an ice bath. The mixture was allowed to settle for 24 hours. The product was filtered under reduced pressure, washed with distilled water until the filtrate became colorless and dried under vacuum at room temperature. Figure shows the scheme. We have a silver nanoparticles, then polypyrrole powder, and exactly how the synthesis of polypyrrole silver nanocomposites has taken place. Now we have completed phase 1 of experimentation. The samples are prepared. Now the prepared samples, we want to know whether they are pure or whatever we have prepared is a correct compound. For that, the characterization is essential. Characterization of polypyrrole powder, polypyrrole polyvinyl composite films and polypyrrole silver nanocomposite was carried out using scanning electron microscopy, transmission electron microscopy, Fourier transform infrared spectroscopy and X-ray diffraction. Let us start with scanning electron microscopy. SEM produces high resolution and 3-dimensional images of surface which provides topographical, morphological and compositional information. This makes them extremely useful in variety of applications. ACM images of samples were carried out using scanning electron microscope JSM 7600F at an accelerating voltage of 10 kV. Here you can see the ACM images obtained of polypyrrole. All the images showed globular structure. Globular particles of polypyrrole with distribution dimension in a range of 0.169 micrometer to 0.73 micrometer were observed. The average size of globules were found 0.60 micrometer. Little variation in size of globular particles were observed for different molar ratios. This agrees with the available literature confirming formation of polypyrrole. The second characterization is transmission electron microscopy, that is TEM. TEM is a vital characterization tool for imaging nanoparticles to obtain quantitative measurements of particle and grain size, size distribution and morphology. The TEM measurements of PPY-AG nanocomposites were conducted on JFM 2100F with an accelerating voltage of 100 kV. The crystal structure of silver was verified by selected area electron diffraction, that is in short we say SAED. The TEM images of polypyrrole silver nanocomposites are shown over here. It is evident from the images that the AG nanoparticle seems to be embedded in PPY matrix. The present method produces spherical silver nanoparticles. Silver nanoparticles are in broad size distribution from 20 to 70 nanometer with an average size of 40 nanometer. The electron diffraction pattern shows characteristic concentric rings as bright spot associated with the silver crystalline nature. The diffraction rings could be indexed on the basis of FCC structure of the silver. Third characterization of the samples is FTIR, that is Fourier transform infrared spectroscopy. FTIR spectroscopy is a technique which is used to obtain an infrared spectrum of absorption or emission of the solids, liquids or gases, creating a molecular fingerprint of the samples. No two unique molecular structures produce the same infrared spectrum. The FTIR absorption spectrum of various samples were recorded using Perkin-Elmer FTIR system in the range of 400 to 4000 centimeter inverse with a resolution of 4 centimeter inverse. The FTIR image obtained for polypyrrole is shown over here. From the image, it is evident that the chemical structure of polypyrrole is confirmed. The type of functional groups present in polypyrrole indicates by the point at which absorption occurs. The broad peak in the range of 3200 to 3500 centimeter inverse, especially at 3429 centimeter inverse, corresponds to NH stressing. The occurrence of small packets at 2920 centimeter inverse ascribed to absorption of band of CH2 group. Peak at 1690 centimeter inverse represents to C double bond. The characteristic peak of polypyrrole is observed at 1538 centimeter inverse, which corresponds to ring stretching mode of carbon and carbon double bond. Bonds located at 1451 centimeter inverse and 1298 centimeter inverse were assigned respectively to CH outplane deformation and CH in-plane vibrations. The peak at 1164 centimeter inverse attributes to NC stretch bonding. Fourth and last characterization of the samples is XRD, that is X-ray diffraction. XRD is a rapid analytical technique primarily used for phase identification of crystalline material and can provide information on unit cell dimensions. Other information that can be obtained by XRD includes crystal size, and perfection chain conformation in amorphous polymers. In present study, the X-ray diffraction pattern was recorded using Philips Expert Pro X-ray generator. Here is the XRD pattern of polypyrrole AG nanocomposite. From the pattern, we can see all characteristic peaks of face-centered cubic structure of silver, namely 2 theta is equal to 38.24, 44.57, 64.51 and 77.45 degrees were observed. Observed peaks are in agreement with those of reported values, confirming the existence of metallic AG in the black powder. No other peaks were observed, indicates that no impurities were present and confirming that the adopted synthesis method gave pure polypyrrole silver nanocomposites. We have finished with all the characterization. Now we have to check, since it is conductive polymer, what is the conductivity obtained of the samples. The picture here is of two-probe conductivity meter used for conducting measurements of the samples. Conductivity measurements were done using the two-probe method. The fine powder of polypyrrole and polypyrrole silver nanocomposite was pressed into pallets at 7 ton per centimeter pressure. The pallets were then coated with conductive silver paste and dried under vacuum before taking an electrical measurement. The electrical conductivity was measured by two-probe method in temperature range 303 K to 343 K. The apparatus used for conductivity measurement using two probes was specially fabricated in our laboratory. Following are the observations on measuring electrical conductivity. The electrical conductivity of PPY is enhanced by chemical oxidative polymerization. The conductivity of PPY depends on ratio of oxidant to monomer. IV characteristic of polypyrrole and polypyrrole silver nanocomposite at different temperatures were studied in order to determine current conduction mechanism in polypyrrole. The temperature dependence of electrical conductivity was studied in the temperature range 30 degrees centigrade to 70 degrees centigrade. Linear relationship of IV curve was found. The electrical conductivity of polypyrrole silver nanocomposite found to be 4.67 into 10 raised to minus 2 Siemens per centimeter, whereas that of pure polypyrrole is found to be 9.85 into 10 raised to minus 3 Siemens per centimeter at room temperature. So the conductivity in nanoparticles increased by 10 folds. Now we come to last part of experimentation, that is application part of the conducting polymers, that is gas sensors. The schematic diagram of typical gas sensing unit is shown in figure. It comprises of detection chamber, programmable multimeter and computer system with necessary software. For measuring gas response, a specially prepared gas chamber was used. The fabricated sensor was fixed inside the gas chamber. The measured quantity of target gas was injected through a syringe so as to yield desired gas concentration in the chamber. The resistance was measured by using scientific programmable digital multimeter. Once the steady state was achieved, recovery of the sensor was recorded by exposing the sensor to fresh air. This was done by opening valve V1 and V2 simultaneously. At the same time, vacuum pump was switched on. Valve V1 allows fresh air to enter the chamber, while valve V2 allows the gas to exit the chamber. The vacuum pump accelerates the process of degassing. All the gas sensitivity measurements were carried out at room temperature. Now let us discuss one of the experiments which we have performed on polypyrrole AG nanocomposite of gas sensing. The nanocomposite was exposed to different gases at fixed ppm of 100 ppm. It was observed that sensor showed more selectivity for NH3 as compared to NO2, CO2, H2S and LPG. To test ammonia gas concentration characteristic, the sensor was exposed to ammonia gas of different concentrations at room temperature in concentration range from 50 to 500 ppm. The gas response values were observed to increase continuously with increasing gas concentration up to 500 ppm. The rate of increase of gas response is relatively higher up to 300 ppm, but response reduces between 400 to 500 ppm, leading to saturation. Important property of a sensor is its reversibility and reproducibility at room temperature. Figure displays the reversibility and reproducibility response of polypyrrole silver composite upon periodic exposure to ammonia. Response time increased from 58 seconds to 153 seconds as the concentration of ammonia increased from 50 ppm to 500 ppm. The recovery time increased from 347 seconds to 746 seconds as the concentration of ammonia increased from 50 ppm to 500 ppm. The testing is finished. Now let us analyze or let us go to the conclusion of the gas sensing what we have studied. The synthesized nanocomposite can be used as a potential material for fabrication of gas sensor operating at room temperature. The response of this polypyrrole silver nanocomposite upon exposure to NH3 was observed by monitoring change in resistance of the nanocomposite film. Sensor based on polypyrrole silver nanocomposite loaded with uniform and small Ag nanoparticles presents excellent reversibility, reproducibility in response. The sensor showed very quick response time of 58 seconds to 153 seconds as concentration of NH3 increased from 50 to 500 ppm. Fast recovery time of 347 seconds to 746 for NH3 gas is observed. The experimental results of NH3 sensing studies reveal that polypyrrole silver nanocomposite films act as electronic nose for ammonia sensing at room temperature. All the work which we have carried for my doctoral degree was published in Thomson Reuters listed journals or UGC listed journals. Here is the Google Scholar profile. We can see our work is accepted by all research scholars nationally and internationally. I have 115 citations. H index is 8 and I10 index is also 5. That is the research work which we have carried out in our laboratory. Thank you very much for your patient listening. Thank you.
ज्ञानेन सदृशं पवित्रमिह विद्यते नहि ज्ञानेन सदृशं पवित्रमिह विद्यते नहि ज्ञानेन सदृशं पवित्रमिह विद्यते